Good morning. Today our next session related to metal forming. We will be discussing about hot and cold working process, which are very important to subdivision process, which are associated with those metal forming. And in the title slide one can find it out, the typical hot rolling, the metal is squeezed and the dimensions are changed in a plastic deformation, and along with it is some water cooling is also done, and with the rollers we will ensure the straightness of all those subjects. Here we will discuss about introduction to hot working and cold working, advantages and disadvantages of hot working and cold working process, because everything is coming out with some merits and demerits. We are doing hot for some advantages, but definitely some disadvantages will come, and vice versa for cold working also. So judiciously we have to select that what kind of process, and which cases we select hot and which cases we select cold, and that is a very important decision. And a person associated with the metal forming, they have to understand that what is the logical assessment of those conclusion towards decision. So considerable insight about the behavior of the metals during forming can be obtained from the stress-strain curve. It is the backbone, it is the Bible. So one has to find it out that what is the stress-strain curve of the concerned material, workpiece material, and how it is behavior pattern. And typical stress-strain curve for most metal is divided into a very important two subdivision. One is elastic one, another one is plastic one. Elastic, easy. That means it will come back to its original. When stresses are given, strain, that is dimensional change, will take place. And if it is in elastic region, it will come back to its original shape. If it is plastic region, it will not come back. So why we are interested about? We are interested about plastic region because we are interested about permanent deformation. We don't want temporary deformation, we want permanent deformation, and permanent deformation has to be done in the plastic zone. So that is why we are very much interested about the plastic zone and the yield strength. Beyond that, it will be a plastic zone, and that will be done in metal forming process. And we are interested about hot and cold because what is the role of temperature in terms of this curve for plastic and elastic region, because if a lot of forces are there, definitely it is better to go for raise the temperature so that the yield strength is less, so that we can reach those plastic region without much hassles. That is the main motivation for hot working, because hot working also coming out with some problems. So this is the typical engineering stress-strain plot. We can see the elastic region and plastic region, and that a mechanical engineer, a manufacturing engineer cannot afford to forget in his lifetime. Even if he is slipping, he will come out of it and find it out that what is the division between those two stress-strain curve. So one can easily find it out. Elastic region, that is a linear one, and the plastic region, after this yield point, it will be a typical non-linear fashion, and maximum load and then fracture. We have to do everything before the fracture. We have to find it out everything before the fracture. If the material is fractured, our purpose is not served. So the y-axis is the stresses and x-axis is the strain, and that is a typical engineering stress-strain plot, and that is differing from different material to material, and we have to find it out what is the tensile strength, what is the yield point, where it will fracture, and elastic and plastic region. In case of metals and other things, it is very much predictable, deterministic. In case of many of the materials, it is not that easy in order to go for that, and there the forming is challenging. So we can sign two stress-strain curve. So elastic region, and that comes from the Hooke's law. The sigma is equal to these E and epsilon, product of it, yield point, and from there itself the plastic region begins and start of necking leading to the fracture. So we have to complete our operations before happening all those kind of problem. Next, we will be discussing about an important problem. This is I have taken from MP Groover of all those worked out example, and this is important for the engineering courses for the students who are associated with these metal forming process. Maybe in the first year also we can show them these kind of problems, maybe in the second year also. And these basic things has to be taken care of in order to understand all those processes related to metal forming. And once the numerical examples and other things will enable the students and everybody to understand all those problems pragmatically with those values, with those units and other part of it. So engineering is associated with mathematics, and if we understand all those numerical formation, and then the understanding will be much deeper, and unambiguity related to the understanding will be minimum. The problem states like this: a tensile test specimen, which is very important for the mechanical and engineering. So we have to prepare tensile test specimen, and that has a straight gauge length of 50 millimeter and a cross sectional area 200 millimeter square. We have to understand the stress strain and their problem associated with that. So gauge length is 50 millimeter and cross sectional area is 200 millimeters. And when the strain, that means dimensional change, definitely these things will change. And during the test of the specimen yields a load of 32,000 Newton. So we are associated with this offset at a gauge length of 50.2 millimeter. So whenever these forces, the gauge length is this. The maximum load is 65,000 Newton, maximum, and reach at a gauge length of 57.7 millimeter. So it is 50, then 50.2, and then 57.7 millimeter, just before necking begins. The final fracture occurs at the gauge length of 63.5 millimeter, final fracture, and determine the yield strength, the modulus of elasticity, tensile strength, engineering state at maximum load, and percentage elongation. Typical problem of all those stress strain relation, and that has to be understood in order to understand the metal forming process, because metal forming is associated with these kind of conceptual understanding. Let's find the solution. So it is illustrated in those figures, whatever we have seen. This industrial stress at any point of the curve is defined as the force divided by the original area, straight, that F by A0. S is engineering stress and F is equal to applied force, and A0 is the original area of the test specimen. Engineering state at any point is given by strain given by L minus L0, whatever the length, then minus original length divided by L0. So that will be engineering strain. That is the basic formula associated with that. And Hooke's law relationship is defined so that E is equal to modulus of elasticity, as known as Young's modulus, and a measure of inherent where stress is proportional to strain, and the proportionality constant is modulus of elasticity, which is known as Young's modulus. And the amount of strain that the material can endure before the failure is a mechanical property. What strain it can withstand before the failure, which I am very much interested about. Why? The reason is, on the basis of that, the metal forming, the permanent deformation will take place. So we are very much interested the material can endure before the failure. And this property of interest is mainly manufacturing process, and common measure of this property, that the amount of strain which the metal can endure before failure, is called ductility. The material which is highly ductile is very useful for metal forming. The ability of a material to plastically strain without fracture. We want to do this strain without fracture. And more the ductility, the more plastically it can deform before the fracture. Less ductility, that means the endurance is less, and much faster the fracture will occur. So we want those materials which are more ductile. Gold is very ductile material. That means it will to plastically strain that material without, so that we can give very intricate shapes in case of gold. The reason is the ductility of gold is terrific. So gold, which is a precious metal, which is lustrous metal, which is some kind of inert metal in terms of oxide formation and other things, and it is a very ductile material. So we can give all sorts of shapes, structures, curvatures, which ladies and girls are very fond of in a gold, and with this luster is there, the formability is great, ductility is great, that means ornable capability is great, and the inertness, that means it will be retained precious material, and other part of it oxide formation will be less. So it is a terrific material. So ductility is also very important in order to give shapes and generate different kind of complex ornaments of shapes and sizes, aesthetically very attractive, original and novel. And the Indian goldsmith and other things, that they are terrific in terms of bringing all those curvature manually, and they are widely reputed extensively all over the world. The reason is the ductility of the gold is terrific. You can give the shape not for the functional design of those things, but for the aesthetic which people can attract with those varieties and novelties. And this measure can be taken either elongation area reduction, and elongation area, all those things can find it out that final length minus original length divided by the original length, and from there itself the elongation is defined. So the yield strength, it comes straight away, that is, we have already gone to the problem, and 32,000 was there, and divided by 200, and it will be megapascal. Pascal means Newton per meter square. So 160 megapascal will be there. And subtracting the offset engineering strain, one can find it out that engineering strain and all those things, it will be these coming out of it, that will be 0.002. Straightway 50.2 minus 50 divided by that 50, and it equals to that value. So rearranging these equations of all those things, we can come out of this modulus of elasticity would be 80,000 megapascal. 80,000 megapascal is E, and tensile strength maximum load divided by the original area. Maximum load is 65,000 divided by these Newton divided by 200, and it will come out to be 325 megapascal. And by those equation of engineering strength and maximum load, it will be 57.7 minus 50 divided by original one, that is 50, and strain has dimensionless. So change with the original 0.154. So all those things putting into those equation, we can define the percentage elongation is 0.19, that is 19%. Very simple, straightforward. Putting all those things, we can come out with those values of those problems. So it is just to understand how the things are going in those way. So in metal forming, the plastic region is of primary interest, because we want to deform those things permanently. Permanency will lead to our domain of interest in the plastic, not in the elastic one. Material is plastically and permanently deformed in this process. And the typical stress-strain relationship for a metal exhibits elasticity below the yield point and strain hardening above it. Yield point, after that strain hardening will be there. There is strain, and it will be the material and the surfaces will be hard and permanently deformed. So here we have those flow stresses. Flow stresses is defined as the instantaneous value of the stress required to continue. Instantaneous value required to continue deform the material. Flow in the plastic state to keep the metal flowing, very important. That is, for the ductile material, that flow stress has to be determined, and it is the yield strength of the metal as a function of strain. What is strain? Dimensional change. So it is the yield strength of the metal as a function of strain, which can be expressed by Y suffix F, flow stress. Y suffix F is equal to K into e to the power n, epsilon to the power n, YF flow stress in megapascal. So that is the basic mathematical formula. So YF is equal to K into epsilon to the power n. So n has a characteristics related to the material. So that will determine the flow stress. So the flow curve is valid. Flow curve is valid representation of stress strain behavior of a metal during plastic deformation, obviously, and particularly for cold working operation. Flow curve. And for any metal, the values of K and N depend on temperature. So if we change the temperature, the value of K and N, the exponent will differ. Sorry, for the strength and strain hardening are both reduced at higher temperature. And that is why we are going for those hot working process. These property changes are important because this result in lower forces and power during forming, because all those heavy power makes the machine very complex, rigid and uncertainties. We are ready to heat all those things and reduce those power, sorry for that, and on the basis of that it will be easy to deform. That is why people are going for those kind of temperature enhancement irrespective of their other uncertainties because of the elevation of temperature. So in addition, ductility is increased at higher temperature, obviously, and which allows allows greater plastic deformation of the work material. And 3 temperature ranges used, I have already discussed in the previous class, that in metal forming can be distinguished cold, warm and hot working process. So cold working, known as cold forming, is metal forming performed at room temperature or slightly above that. So no hassles for temperature enhancement. Advantage, significant advantage. First advantage is that you don't have to heat it. So that is the first advantage, but in terms of yield, the advantage is greater accuracy, meaning closer tolerances can be achieved. Dimensional uncertainties are less. If you heat the material and other things, dimensional uncertainties, stress relieving and other things will be there. Dimension will change. So we don't want that for precise manufacturing. So cold working is suitable for precise manufacturing. Greater accuracy, meaning closer tolerances that can be achieved. Better surface finish, because hot working, sometimes oxide formations and other things are there at elevated temperature. Oxides are easily formed, so better surface finish will be obtained in cold working than hot working. Higher strength and hardness of the part due to strain hardening. The surface and other things are already hardened, so that we don't have to do some kind of case hardening or surface hardening operation related to those process. And grain flow during deformation provides opportunity desirable. The grain structure growth and their formations is desirable for those strength in terms of those materials. They are aligned appropriately along with some linear directions. And directional properties to be obtained because the directional properties are sometimes very important for the metallurgical point of view in order to bring the better microstructure for the sustainable behavior of those patterns. And last, I have already discussed in the first, the heat is giving heat is always a challenging option. So no heating of the work is required, which saves furnaces, fuel cost, permits, higher production rates, and all those tools and tackles has to be not to be very other kind of material, heat resistant type of material. So that is always a terrific advantage. So owing to these combination of advantages, many cold forming processes have become important for mass production operation. Terrific advantages, unique selling point of cold working, many selling point of cold working. Close tolerances, good surface finish, minimize amount of machining required. People don't want to do it at one step. So further post-processing minimum, that is always advantageous, always less hazardous, less cumbersome. in order to do that. And these operations can be classified as net shape or near net shape manufacturing. People are looking for net shape or near net shape so that post-processing hazards are less. I want to do it in one go. Otherwise, it will be a problem. But there are, why every process is not cold working? The reason is there are disadvantages, and the disadvantages or limitations associated with cold forming operations are higher forces, higher yield strength, higher forces, machine has to be dinosaur, and whenever higher forces, linkages and all those things becomes very, very cumbersome. Huge amount of power required to form those operations. That makes the entire situation very clumsy and cumbersome, and must be taken in to ensure that the surface of the starting workpiece are free of scale and that. So while processing, those kind of modification may not be easy. So the workpiece are free from dirt and scale has to be ensured that, otherwise it will be a defective product. But in case of hot working process, that can be taken care of because of the elevated recrystallization. Here the recrystallization will not take place, so that is why one has to be very sure about the quality of the input material. And ductility and strain hardening of the work material limit the amount of forming that can be done, because strain hardening sometimes little bit defeating. The reason is that it will make harden and the formation capability will be less. So that also sometimes a difficult proposition also. So one has to look for those things. Then warm warping, because of the plastic deformation properties are normally enhanced by increasing little bit of temperature. Forming operations sometimes perform at temperature somewhat above the room temperature, because temperature will lower the yield strength. But below the recrystallization, beyond the recrystallization, there are some issues, so one can compromise with that. Warm warping applied to these second temperature range, between room temperature and below the recrystallization. Dividing line between cold working and warm warping often expressed in terms of the melting point. So melting point is a very important property of those materials, and dividing line is usually taken to be 0.3 of the Tm, T suffix m, where Tm is the melting point in absolute temperature of the particular metal. So within that 30% of the melting point in absolute temperature will be warm working. Then we come to the most important part of that is hot working, also called hot forming. Involves deformation and temperatures above the recrystallization. Why we do it? Because lowering of those yield strength. When the yield strength will lower? When we reach recrystallization temperature, but before and the yield strength will be manageable, so that our machines are moderate. So we are ready to compromise in terms of temperature. The recrystallization temperature for a given metal is about 1/2 of its melting point on absolute scale. Mostly it will be near about that, 50%. Warm working in 33% of those things in absolute scale of the melting point, and recrystallization is half of it. And practice hot working usually carried out at temperature somewhat near about half of those melting point in absolute scale. So the work metal continues to soften because of the temperature, because of the random motions of all those things. It is easy to soften. It is softened and enhance the advantage of deformation. The deformation process generates heat also and increases the work temperature in localized region of the part. That will make the life easy, and this can cause melting in these regions, which is highly undesirable. So sometimes it will make more ductile, but sometimes whenever it reaches, because of the temperature, reaches to the melting point, that is undesirable. That formation will be jeopardized. So one has to be pretty cautious, because working also generates some temperature. And also scale on the work surface is accelerated at higher temperature, obviously, because elevated temperature, oxide formation possibility is much more. So the scaling will be there, scaling not a desired one, it will jeopardize the surface finish, it will also hamper the accuracy and precision of those products. So accordingly, hot working temperature usually in between those, within the range of 0.5 to 0.75 of the melting point of those metals. So most significant advantage of hot working is the capability to produce substantial plastic deformation of the metal far more than possible with cold and warm working, because cold and warm working lot of efforts. So some stubborn material is not ready to deform easily at lower temperature. Lot of force is required. So it is better to elevate the temperature so that they are negotiable in terms of deforming. And principal reason for this is that the flow curve of the hot work metal has a strength coefficient that is substantially less than at room temperature. Those things K and N have a role to play. And the strain hardening exponent, those things are favorable, and the ductility of the metal is significantly enhanced, and that is why we are doing that. So all of this results in the following advantages: that shape of the work part can be easily altered, so easily deformable, easily shape can be parted. Lower forces and power are required to do, that is, the machines will be much more miniaturized than the conventional one, because less force will be required. Metals that usually fracture in cold working, because huge amount of stress at room temperature, fracture possibility is there, it cannot be fractured at lower temperature with lower force. Strength properties are isotropic in nature, it will be homogeneous. Grain structure typically created in cold, forming some directional part. Here it is isotropic and no strengthening of the part. So because of the above recrystallization temperature, strain hardening will not occur. So that means easy to deform. Sometimes strain hardening is a defeating process for the cold working because of its hardening effect. That is a great advantage of hot working process. This last advantage is seen inconsistent, because sometimes the strengthening of the material is often considered an advantage where we require, and sometimes so some kind of compromise has to be there. So some advantages, and that is a application based decision. There are applications in which it is undesirable to be metal to be work hardened. If you want to do some kind of post processing, it is not. Ductility is reduced. So those kind of things are also not desirable in many such applications. So people have to be judiciously using those kind of features. Disadvantages, definitely hot working has disadvantage, otherwise all working process will be hot one. Lower dimensional accuracy because of the stress relieving and recrystallization temperature. Stress relieving dimensional inaccuracies will creep into the system, and that is not desirable. One has to do some post processing, one has to be very alert about manufacturing of the precise products. Higher total energy required, obviously, because the temperature is raised, and thermal energy, so higher energy will be there. Work surface oxidation, again obvious, because at elevated temperature the metal will form the oxides. Possibility is more, so scale will be more, and scale is not at all an intended one, because scale is removed, dimension distortion, surface finish will be problem, accuracies will be problem, and obviously the hot working will have a poorer surface finish in comparison to the cold working process, and shorter tool life, because tool also has to be heated, and whenever it is heated, even it is made of high strength and temperature resistant alloys, it will also have some deformation related to that. So some kind of special alert has to be there, and tool life will be less because it has to negotiate with the metals and materials at elevated temperature. So recrystallization of the metal in hot working involves atomic diffusion, is a time dependent process. It has some time relationship. These can be often performed at high speed, do not allow sufficient time for complete recrystallization, incomplete, and during the deformation cycle, and sometimes there is a problem. If you can put it into the scanning electron microscope, one can find it out, all those things. High temperature recrystallization eventually does occur, and it may occur immediately following the forming process or later as the workpiece cool, because of the temperature and time dependent phenomena, some changes in microstructures. Even though recrystallization may occur after the actual deformation, it is eventual occurrence, and the substantial softening of the metal at high temperatures, features of distinguish hot working from warm working or cold working. So even after these operations and other things, these will also happen, and this is the difference in warm, cold and hot. So that's all today. We have discussed about in details the basic difference between cold and hot working and warm working, their features in details, and we have discussed with some of the problems and numerical examples which is associated with the metal forming process. Just a very basic and rudimentary examples, and we found it out what is the role of temperature in terms of the yield strength and why we go for hot working and what kind of conditions and other part of it and why it is favorable, and we have got some idea of the ductility and other part of it, and we get a fair idea about the distinction between these two processes in terms of application. Thank you very much for your patient hearing.